In this example problem, we have an archer shoots an arrow horizontally at a target 15 meters away. The arrow is aimed directly at the center of the target, which I've put a big red blob here where the center of the target is, but it hits 52 centimeters lower. What was the initial speed of the arrow? Okay, so before I even start adding information to the picture that I have drawn below, I'm going to go ahead and make sure that all of my units are consistent in this problem. Okay, because you can see that the horizontal distance is given as 15 meters, and the vertical distance that this arrow travels is 52 centimeters. So my first task here is to convert 52 centimeters to meters, just to make sure that everything is consistent. So I'm going to go down to the bottom left-hand side of the screen. I'm going to write 52 centimeters. Okay, now I'm going to divide that by 1, just following the procedures for converting units that we covered earlier this year. And I'm going to multiply this by the conversion factor that will convert centimeters to meters. So just in case you forgot, a quick Google search shows us that there are 100 centimeters in a meter. Okay, now since centimeters is up top, I know that my centimeters needs to go on the bottom. So 100 centimeters is equal to 1 meter. And that conversion factor will take us from centimeters to meters. So that's all I have to do. So it's equal to, all right, so I'm multiplying two fractions, so multiplying straight across the top. That's 52 times 1. Okay, that gives me 52 up top. Okay, let's not forget about our units. Centimeters times meters. Okay, that gives me centimeters times meters. Okay, all divided by, okay, we multiply straight across the bottom now, so 1 times 100. It's going to give me 100 on the bottom. Okay, my first denominator is dimensionless, so nothing times centimeter leaves me with centimeters. Now, it's really easy to see if we treat our units just like they're numbers or variables. We've got centimeters divided by centimeters, so my centimeters cancel, and I'm left with just meters, which is what I want. All right, so 52 divided by 100, okay, that is 0.52, and then meters, which is the only unit that I have left over. Okay, so now let's draw this on our picture. All right, so that is my vertical distance that the arrow drops. Okay, so whenever this arrow hits, it hits 0.52 meters below the center. So that is my vertical drop. So we'll call this YF, because it's in the vertical direction, is equal to 0.52 meters. Okay, that's how far it drops. All right, now another piece of information that's given in the problem is that the archer shoots an arrow horizontally at a target 15 meters away. All right, so let's define our origin here before we do anything else. So I always like to put my origin right where the object starts. So I'm going to put a little O here for origin, right at the center of mass of the arrow, and that's where I'm defining the initial position. Okay, and so the x component of the initial position and the y component of the initial position, that's where they're going to equal 0. Okay, so now we're given that the target is 15 meters away from the arrow. Okay, so drawing this on my graph from the origin, I've got my horizontal distance that it travels. So xf is equal to 15 meters. All right. Now, we know that when this arrow is shot, that it will follow sort of like a curved trajectory here. So I'm just going to draw a dotted line, okay, showing that it bends down slightly and then hits at that point. Okay, so since it is moving down from the origin in the y direction, I know that this 0.52 should have a negative sign out front. So just go back to that YF and throw in that negative sign. All right, because I waited to put that in there because this can change all depending on where you define the origin. But because I'm defining the origin where the arrow begins, okay, it falls from the origin downward, so that should be a negative sign with that 0.52 meters. Now, there's some other information about the problem that we know that's not explicitly stated. For instance, I know as soon as this arrow leaves the bow, I know the only force acting on the arrow is the force of gravity. Okay, so since the force of gravity points straight down, I know that my acceleration, okay, in the y direction is going to be negative 9.81 meters per second squared. Now, since it's perfectly downward in the y direction, I know that the x component of my acceleration is going to be equal to 0. Alright, so I know it's getting a little bit tedious here, but I want you guys to get into the habit of drawing as much information on the pictures that you draw as possible. So I also know that when this archer shoots this arrow horizontally, that the initial velocity is perfectly horizontal at the beginning. So whenever this arrow is first shot, the initial velocity is perfectly horizontal. Alright, so the initial velocity vector, okay, is equal to the initial velocity x component, and we don't know what that is. Okay, so since the initial velocity is perfectly horizontal, I know that my initial velocity in the y is equal to 0. Alright, so this arrow travels this trajectory until it hits the target down here at this point. So since the acceleration in the x direction, okay, is 0, we know that the velocity in the x direction should not change because the acceleration is a change in velocity. Okay, so whenever it hits way over here, I know that my v final in the x direction, okay, is going to be equal to my initial velocity in the x direction, which we do not know. But it's just a good piece of information to write down just in case there's like a follow-up to this problem. Okay, but I do know that the velocity is going to change in the y direction because my acceleration is in the y direction. So we also don't know what that is. So Vfy, we do not know what that is, but we know that it's going to be different than the initial velocity in the y direction, which was 0. Okay, so now that we have our problem set up, and really this is probably the hardest part of the problem, and that is choosing the correct kinematic equation to solve for the information that we want. Okay, so what I want you to do is pause the video and go back to our equations of equations of motion summary sheet that I gave you on the in-class notes, and just take a moment and try to finish this problem on your own. Okay, and then after you think that you have a good answer, or if you get stuck, then play the video and watch how I solve for the initial speed of the arrow. Okay, so now hopefully you have given this problem a go, and I've already picked out the equations of motion that we need, and I've written the two equations of motion, the two kinematics that we need to solve this problem, and I've also rewritten all the information in the y direction that we know, and all the information in the x direction that we know. Now you can see that when I plug in my initial position in the y, okay, the first term is going to go away because it's 0, and also because the initial velocity is perfectly horizontal, I know that my y component, when I plug it in, is going to make the second term go to 0. Alright, so I've got yf here that I can plug in for yf. So I've got negative 0.52 meters is equal to, okay, 0 plus 0, I'm just going to leave those off, okay, is equal to 1/2 times, all right, the acceleration in the y direction, which is just the acceleration due to gravity. So negative 9.81 meters per second squared times t squared. Okay. Now you may be saying at this point, well, why the heck did I do that? Because the only thing that I can solve for using this equation is the time. Well, that's because we need the time to plug into the other kinematic to solve for my initial velocity. Okay, so just hitting this with an algebra stick. I'm not going to walk through all the details of how to solve for this because I think you guys can do it at this point. But just rearranging this equation and solving for t, what you find is that the time is equal to approximately 0.32325. Okay, now I'm not rounding this yet. I never round anything until the very end. So I just cut it off at 3 just to help me keep track. But when I plug this time into my other kinematic equation, I'm going to use the 0.32559832, that whole big number in my calculator. Okay, so now I know the time, and since it is a scalar quantity, I also know that the time is going to apply to my other kinematic. So my time over here is 0.325 in seconds. Okay, now you can see that when I plug in my initial position in the x, first term goes away. When I plug in my acceleration in the x direction, okay, and for ax, the third term goes away. So now I've got a relatively easy equation that I can use. So xf, okay, actually let's go ahead and plug in xf. All right, we know what xf is, so let's go ahead and plug that in. So we've got 15 meters for xf is equal to, okay, v naught x, I don't know what that is. So v naught x times t, which we just solved for. So times 0.325 seconds. Okay, rearranging and solving for v naught x, I find that my initial velocity in the x direction is approximately 46.06 meters per second. Okay, now whether you realize it or not, that is my final answer, because remember what we said. Okay, since our initial velocity is perfectly horizontal, then when I solve for the x component of my initial velocity, that is equal to my initial velocity vector, but only because my initial velocity is perfectly horizontal. In the next section, we'll look at how this part of the problem changes whenever we have a launch angle, which we don't in this case. Okay, so we know that this is also going to be equal to my v naught. So my initial velocity vector is 46.06 meters per second. And finally, watching my sig figs here, I get an initial velocity that is equal to 46 meters per second. And that's my final answer. Okay, so if you have any questions, just feel free to ask.